So basic vectors in a plane. So remember that vectors can be expressed in terms of unit vectors, ij in 2 dimensions and ijk in 3 dimensions. These vectors form a basis for 2 or 3 dimensional spaces in which vectors exist. And so I, j, and k are called basic vectors. So vector u, which is the same thing as vector OP, or the resultant, is equal to a times vector I plus b times vector j plus c times vector k. Therefore, all vector rules discussed in the previous chapter apply for algebraic vectors as well. So two algebraic vectors are equal if and only if the respective Cartesian components are equal, and two algebraic vectors are collinear or parallel if one vector is a scalar multiple of the other. And we learned this from the previous unit, where vector u is equal to just a scalar k times a vector b. So again, commutative property, addition property, scalar property, all are the same when it comes to vectors as well. So when it comes to scalar multiplication in two-dimensional space, m times vector OP is equal to m in the point AB, which is just m times A and m times B. So again, you're just literally filling it in. Or m times a vector OP is equal to m times a vector I plus b vector j is equal to m times a vector I plus m times b vector j. So in 3D space, it's the same thing that applies. Again, scalar multiplication, FOIL that thing in. Now, vector addition and subtraction, similar to like collecting like terms in polynomials. So we have a1, b1 plus minus a2, b2, which is equal to a1 plus minus a2, or b1 plus and minus b2. Or if it's in a three-dimensional space, all you're really adding is that c. So you're just going to get c1 plus c2 at the end. So the first one is my scalar, 7 multiplied by the point, 3, negative 5, negative 9. Who can tell me what the new result is if I factor in that scalar into my original point? What would it give me? It's like distributive property without the algebra. (21, negative 35, 63). Thank you. So this would be a parallel vector because it's just a scalar of the original one. Now the next one, we have negative 3, 4, and 5, plus 5, minus 2, and negative 6. So again, simple addition. So we get negative 3 plus 5, comma 4 plus negative 2, comma 5 plus negative 6. Who can tell me what my new vector is going to be? Two, 2, and negative 1. Perfect. All right, we got the easy stuff out of the way now. Now let's get into a bit more of not challenging questions, but more application type of questions. So we have vector u is 3 and negative 5, and vector v is 2 and negative 1. So this is a two-dimensional space. I want you to determine for A what vector 3v is going to be. So who can tell me what vector 3v will be, for example, 1a? Remember, all you're taking is vector v and multiplying it by 3. 6 and negative 3. Thank you for the answer. So it's 3 times 2, negative 1, which gives me 6, negative 3. Perfect. Now I have b, which is 2 times vector u minus vector v. So I'm taking my vector u, multiplying that by 2, minus vector v. So take a couple seconds to compute that and tell me what my new vector is going to be. Everyone forget there was night school today? Anna, Rabia, Samuel, and Ian that are still absent. Did anyone else get 4, negative 9 for question, for example, 1b? Everyone, did anyone else get 4, negative 9? Anyone? Okay, perfect. And then the last one, I need to find the magnitude of vector u plus 2 times vector v. I'm going to take my magnitude, so I get vector u, which is 3 and negative 5, plus 2 times 2 and negative 1. And remember, guys, we have to find the magnitude of that. So my point becomes the magnitude of 7 and negative 7. So who can tell me what the magnitude of u plus 2v gives me? Let's see if you guys can calculate this and figure it out. 7 root 2. So Priyanshu got it pretty fast. Did anyone else get to that point yet? Okay, so Priyanshu probably got equal to the square root of 98, which is equal to the square root of 49 times 2, which gives me 7 root 2. So that would be the magnitude of u plus 2v. So now we need to find the components of algebraic vectors between 2 points. So reposition of the following vectors. So reposition the following vector so that its initial point is at the origin and determine its components. Okay, so you have my vector p, which is the tail, and q, which is the head. Okay, so I need to start these all at the origin. Okay, this is going to be O. I need vector OP, and I need vector OQ. So I need to somehow figure out how to get vector OP So based off the information I have so far, I know P is equal to -1 and 2, and I know Q is equal to -4 and -3, based off the points of my two-dimensional shape. So I need to figure out my vector PQ. What is PQ? So again, I know P is my head and P is my tail and Q is my head. So in order for me to figure out what vector PQ is, I need to take the point of the head and subtract it by the point of my tail. Which means that vector PQ is going to be OQ, vector OQ minus vector OP. So I know my point P, which is OP, is negative 1, 2. And my point Q, which is OQ, vector OQ is negative 4 and negative 3. So I'm going to use what we learned from vector addition and subtraction, which is negative 4 and negative 3 minus vector negative 1 and 2. So who can tell me what my vector U or PQ is going to give me? So who can tell me what vector PQ is when we take OQ and subtract it from OP? Negative 3 and negative 5. Which means that my vector U, which is my resultant, is going to be negative 3 and negative 5. Now, what if we have a three-dimensional space? So for B, I have my resultant vector, which is P over here, and Q, which is all the way up here. So I need to figure out, based off my origin, I need to figure out what P is and what Q is. So I need to figure out, how do I get from O to Q, and how do I get from the origin to P? Does anybody want to take a stab as to what my point P is? So remember, my point P has to do with this parallelogram on the bottom right-hand corner. So remember, if we're going to point P, I know that my y is 7, so I know y is 7. My x is going to be positive 2. Add my z is negative 6, which means that my point P is simply just, so this is 7, that's my bad, 7, negative 6. I drew this way too. Supposed to end. Which means that my P the reason I know it's 2 is because of this point over here, 2 and negative 2 and negative 2. And because it's going into the negative, and because it's going in the other way, it means it's positive 2. So again, I'm referencing based off of this point that it makes right here. I know it's hard to see, but I think on your computer you can see that if you were to come up with a 2D point for x, that line intersects at -2 and -2. Which means that P gives me 2, 7, -6. Now, using this information, I want you guys to try to figure out what Q is going to give me. Again, based off of the origin. So again, I'm going to erase this because we found P. Now I want you guys to find Q. Again, it's a bit harder to see because there's a bunch of crap being drawn in between them. So who can tell me what Q is going to be? Let's see if you guys can figure this one out. Close, Ricardo. Remember, I know it's weird, but even if it's going to the left, which part of the x-axis is positive? The top part or the bottom part? The x-axis in the 3D space is opposite from what everything else is. So what should my first point be? 1. So my Q is going to be 1, -4, and 7. Remember, guys, this is my negative x-axis right here, going to the right, and this guy is my positive x-axis over here. I know you guys are used to going to the left, which makes sense, which is why you would assume it would be negative, but in this case, it is not. So remember, we said my vector PQ is equal to OQ, vector OQ minus vector OP. So if you guys were to do vector subtraction with 1, -4, 7, minus 2, 7, -6, what would my vector PQ give me as a result when I do this vector subtraction? What would it be? Who can tell me what vector PQ is going to be? Thank you, Ricardo. -1, -11, 13. Perfect. Beautiful. So again, as you can see, it might be starting to become a bit easier. There's going to be more examples like this later on. So given 2 points in 2D space, px1, y1, and qx2, y2, we can find the position vector, which is equivalent to a related position vector. So the magnitude of PQ, which is equal to the magnitude of vector OA, is equal to x2 minus x1 squared plus y2 minus y1 squared, which is equal to the square root of a plus a squared plus b squared. And same thing can be done with three-dimensional spaces, which means you're going to get the magnitude of PQ, which is going to be the square root of a squared plus b squared plus c squared. So is the order important when finding PQ? As we've seen from our previous examples, yes it is. Because we're always going from, it is always head minus the tail. Okay? So vector PQ is not the same thing as vector QP. So example 3, so if A is 14, negative 7, and 9, and B is negative 3, 16, negative 8, are points in the space, I want you to calculate each expression. Okay, so I wanted to calculate vector AB. Remember, A is the tail, and B is the head. So I want you guys to calculate vector AB for me and tell me what it is going to be. So given that vector AB is equal to OB minus OA. So I want you guys to try and figure out what my vector AB is going to be given the 2 points that we have. Type in your answer in the chat, please. Once you have your answer, feel free to type it in the chat, please. Thank you, Priyanshu. It is going to be negative 17, 23, and negative 17. Perfect. Now I want you guys to do the same thing to find vector BA. So again, this is just OA minus OB. So if you guys can do the vector subtraction, what is my vector BA? What is that going to give us? Thank you, Lauren and Ricardo. It's going to be 17, negative 23, and 17. So if we were to compare the direction of these vectors, what would they be doing? Would they be going the same direction or the opposite direction, given what we just found? Opposite. So these two guys over here are going in the opposite direction, which is why vector AB or vector PQ is not the same thing as vector QP, because they do not give us the same resulting vector. They give us vectors going in the opposite direction. Now, let's take a look at what the magnitude of vector BA is, given what we found. So it's just going to equal the square root of 17 squared plus negative 23 squared plus 17 squared, which gives me the square root of 289 plus 529 plus 289, which gives me 1,107. I can break this down even more by doing 9 times 123, and that gives me 3 root 123. So that would be the magnitude of vector BA. Now, can someone tell me what the magnitude of vector OB is going to be? And when you have the answer, please type it in the chat. Can anyone tell me what the magnitude of vector OB is? Yep. Thank you, Priyanshu. It is the square root of 329. Perfect. So using vectors, we want to demonstrate that 3 points D, which is negative 5 and 43, and E, which is 5 and negative 2, and F, which is 3 and 7, are collinear. Okay? So I have my D, which is over here. I have my E, which is over here. And I have my F, which is right here. So in order for me to prove that they're collinear, I need to figure out if DE is equal to a scalar of DF. That's what I need to prove. So first of all, I need to figure out what my vector DE is going to be. So vector DE is going to equal to 5 and negative 2, subtract negative 5 and 43, which gives me a result of 10 and negative 45. Now, I need to figure out what my vector df is going to be. So I want you guys to help me out and try to tell me what vector df is going to be by taking vector OF and subtracting it from vector OD. So who can tell me what vector df is going to give me? So again, we're proving this. Once you have the answer, please type it in the chat. Eight and negative 36. Thank you, Pianchu. This is going to be 8 and negative 36. Perfect. So I need to prove that vector DE is equal to k times vector DF. I'm going to take vector DE, which is 10 and negative 45, and have that equal to k times 8 negative 36. We're going to use our scalar. So now what we're going to do is we're going to take each one as is. I'm going to do 10 is equal to 8k. If I simplify that, I get k is equal to 5 over 4. Now, in order for this to actually determine if it's collinear, negative 36k equal to negative 45 has to also give me 5 over 4. And when I simplify it, it indeed gives me 5 over 4, which means vector DE is equal to 5 over 4 vector DF, which means they are collinear. Is everyone okay with this example? All right, we're going to do example 5 and 6, and you guys are going to do example 7 on your own. Okay, so in example 5, we want to find a unit vector in the opposite direction of vector u, which is 3, 7, and negative 1. So remember, a unit vector from last unit is just equal to 1 over the magnitude of u times my vector u. So I need to find my magnitude of vector u, which is equal to the square root of 3 squared plus 7 squared plus negative 1 squared, which gives me 9 plus 49 plus 1, which gives me the square root of 59. Which means my unit vector is going to be 1 over square root of 59, times 3, 7, and negative 1, which gives me 3 root 59, comma 7 root 59, comma negative 1 root 59. Or if I want to if I want to bring the radicals to the top, it's just 359 over 3, 7 root 59 over 59. That's my apologies. Do not listen to me on that one. It should be 59. And negative root 59 over 59. So this is for unit vector u. Now I want it in the opposite direction, so I need to figure out what negative vector u is going to be. So who can tell me, based off our unit vector u, what my negative unit vector u is going to look like? Literally, what do I just have to put in front of each of these numbers, or each of these points? When it's the opposite direction, all we're doing is flipping the sign. So my unit vector in the opposite direction is negative 3 root 59 over 59, negative 7 root 59 over 59, and positive root 59 over 59. So this is my unit vector in the opposite direction. Oops, what am I doing? And then the last example that we're going to do is parallelogram OPQR has its sides determined by OP. Remember, our origin is always at the bottom left, so this is O. So OP is 1, negative 4, and 2. OQ, OR, is going to be negative 4, 1, and negative 1. Its fourth vertex is point Q. I want to determine the components of this point. Okay, so again, this is the way my vectors are going to be going. And I want to figure out its fourth component, which is Q. So what I'm figuring out is OQ. So I know vector OP, given by my description, is 1, negative 4, and 2. Vector OR is negative 4, 1, and negative 1. So now I need to figure out what OQ is going to be. So OQ, from what we know from last lesson, is going to be vector OP plus vector OR. Because remember, the resultant from last unit was A plus B gives me vector U. So I take OP and add OR, I get negative 3, and 1. Which is what this point over here is going to be. This guy over here is negative 4, 1, negative 4, or negative 1, sorry. This guy is 1, negative 4, and 2. So which means that my components of this point is going to be negative 3, and 1. which is exactly what we need. Okay? So that's how you would find the components of that point, is taking OQ and making it equal to OP plus OR. Because back from, I think, the last unit, it was A plus B gives me vector U. Which means that my vertex Q is equal to -3, -3, and 1. Okay, so -7, you guys are going to do on your own right now. Well, not right now, but at the end of class.